Can you see online, or is there like a blank square? Oh, we're good.
No square.
Perfect. Okay, so as Jake said, my name is Farrell Helbling. I am an assistant professor in ECE at Cornell University. I work with the robotics program there. I work on insect scale vehicles. This is some of the work that I completed towards the end of my PhD and beginning of my postdoc on creating power autonomy for these small scale systems. And I'm actually going to break down the problem into all the various components of what our power supplies need to be. I didn't even see it. Okay. What our power supplies need to be, how we actually build our step-up converters for the small scale actuators that we have, and then the total vehicle redesign that needs to happen at the scale. So there's always these inherent trade-offs between the electrical and the mechanical system. So we really have to co-design both of these platforms together. Okay, we don't just have a mechanical system that we can then attach additional mechanisms to. Everything kind of has to come up at the same time. So science fiction has this idea of like what we can do with small insect scale vehicles. Black Mirror, for about one entire year of my PhD, really ruined my life. Just because everybody sent me the clip of Hated in the Nation, which wasn't even about RoboBees. It was just the tool that was used to hurt people, but was not about robotic vehicles. At approximately the same time, Eye in the Sky came out. This is a stealth beetle-sized drone. I was at the World Economic Forum giving a presentation, and I think this was on the flight over because every single person asked me about this. GI Joe Retaliation, they were using a Firefly. Do I have Minority Report? Okay. And then Minority Report in 2002, this got me excited about insect scale robots as a kid. How many of you guys have seen Minority Report? God, only one. You should watch this movie. This movie is very good. It was a book. It is a movie. Would recommend. This, they like throw discs on the ground and then they come up into these crawling spiders and they're able to look around this building. Richie Rich came out when I was very young. I do not remember this movie in theaters. I am not that old. But the thing that I love about Richie Rich is that the scientist has built this prototype. It's so stable that he gives the robot to this novice who's never flown it before, and just with a single joystick is able to fly it around the room. Not well. I mean, obviously he flies it into the butler, who's very annoyed and breaks this probably multi-million-dollar prototype. But this is not something that we can currently do with our systems, right? It takes years of expertise and training to be able to fly the vehicles that I work with, as some of my students who are on this call now. But if you think about off-the-shelf, like robotic platforms, they're plug and play, they're modular, and they're robust. And we can answer a lot of questions in terms of planning and estimation, in terms of locomotion capabilities, using these systems, right? You can find them in dozens of labs across the country. KUKA robot arms, I don't know if you guys have exactly KUKAs upstairs, but you certainly have a bunch of robot arms. I mean, Cassie is being used by Michael Pose's group here. Minotaur from Ghost Robots, that was something that came out of the Grasp Lab. Little Dog from Boston Dynamics, Spot Mini from Boston Dynamics. I mean, the Da Vinci research kit has really revolutionized minimally invasive surgeries. And then the Crazy Fly, you know, as something at small scale, but quad rotor technology is ubiquitous. Micro robots, however, insect scale robots. I should be careful about micro robots because now that Mark Niskin is here, you guys actually do micro robots. Insect scale robots, they're delicate, they're tethered, and they're incredibly specialized. So if you're in this field, right, I can look at this slide and say, I know exactly who made all of these robots, right? There's nothing, there are a lot of things that separate these different manufacturing strategies, these different actuation strategies, and how they can actually move. What you'll notice is that in every single one of these pictures, except for this Niskin photograph, every single one is tethered, okay? And that really limits the use cases for other researchers. It limits the use cases for us, right? I can only go as far as my tether allows, right? I also need to think about the stiffness of my tether, okay? To say, how is this actually going to affect my control strategies? There may be interesting things that we can do with our tethers and kind of add it as a feature and not as a bug. But for now, when we think about, any task or application that we have for micro robots, we want them to be able to work in any type of environment. And currently, they're not able to do that. So if we want to make an autonomous micro robotic platform, right, we need to answer these fundamental questions in micro and mesoscale manufacturing paradigms, which I'll talk about today, specifically laminate-based manufacturing and pop-up book mechanisms. Power storage and amplification is a problem across all of robotics. It is an especially large problem as you start scaling down. A lot of the chemistry just isn't there. And a lot of the packaging that is required is very heavy. And that limits use cases for batteries. Okay, so RoboBee is 80 milligrams without any electronics on board. The smallest LiPo battery that I can buy off the shelf is 330 milligrams. Okay, so my power system is 5 times the weight of my actual system. That limits what I can do. Also thinking about new custom sensors and ICs. This is not so much of a burden at the moment, just because of everything that is going on with the cell phone industry, with the wearables industry. We're getting smaller and smaller sensors. We're getting smaller and smaller ICs. So a lot of the work that I've been doing is actually integrating a lot of off-the-shelf components together for new purposes. But once you have these systems, you can start thinking about interesting locomotion strategies. So I'll touch on this a little bit at the end of the talk. Because we are so small scale, we get to leverage surface forces. Okay, so we can leverage friction, stiction, any type of adhesive force, right? And so I can climb upside down if I want to. I can climb up walls if I want to. I can walk on water if I want to, which is something you can't do with heavier systems. We can also think about collectives. Each of these robots costs about $10 in material parts. They cost thousands of dollars when you think about, all the specialty required to do it. But if you could actually figure out a mass manufacturing system, you can start thinking about robot collectives. You can think about collective algorithms, and you can think about, a diverse heterogeneous swarm as well. You can build some robots that can crawl, some robots that can fly, some robots that carry different sensing capabilities. You can create a diverse sensor network. Also be used as a platform for biological study. It is super annoying to get bees, stuff them into straws, and then whip them around in these tubes to understand exactly how their wings bake and bend and how frequently they need to hit the wall, right, in order to actually get damaged. You can do the same thing with a small-scale robot. You can come up with strategies for planning and estimation, especially for low compute resource constrained systems, and then doing the entire system level optimization. Okay, so a lot of what I do is systems engineering and looking at the trade-offs between the mechanical and the electrical systems. Okay, so 10 years ago when I started my PhD, this paper had just come out in Science. I'm sorry that it's a little bit dark, but this is the RoboBee. The mass of the vehicle is about 80 milligrams. It has a wingspan of about 3 centimeters, but that is really contingent on the speed with which we are flapping. You could make it smaller, you could make it larger. Using wingspan as a metric is a little bit challenging. It has a flapping frequency here of about 120 hertz. This will change over the course of the talk. Do not fret, it's just an updated vehicle design. It uses 2 piezoelectric actuators that operate at about 180 volts. It has a payload capacity of only 40 milligrams, so one single IMU sensor can fit on board this vehicle. And it consumes about 20 milliwatts of power. Okay, 80 milligrams, if you're not comfortable with numbers as small, it means that it takes 32 of them to weigh a penny. Okay, they're incredibly lightweight systems. 4 years ago, which is what I worked on, like right before the pandemic hit, was the first untethered flight of one of these vehicles. So designed a completely new system. The mass is now 90 milligrams and is a 4-wing, 2-actuator vehicle. And I'll explain why later in this talk that is important. It has a slightly larger wingspan just because of the mating connections. It can carry it has a payload capacity of about 200 milligrams compared to the first version. And consumes about 28 milliwatts of power just because we're trying to get all of the force out of these actuators that we possibly can. Basically, as the light turns on the top, there's a photovoltaic array that you see here. It's so far from the top of the vehicle just to eliminate any ceiling effect, and make sure that we're achieving all the vertical lift that we need. There's a signal generator on the bottom. That's that yellow PCB that was custom made in-house. I made probably 10 of them. They all worked. It was great. It weighs about 90 milligrams and consumes about 110 milliwatts of power. Okay. This is an incredibly dumb system. Okay. As soon as it sees light, as soon as the microcontroller gets power, it just executes the flapping strategy. Okay. As soon as it leaves the light source, which it has done, it has left the field of vision, it will just slowly start to fall again, back down. As soon as it sees light again, it will start flapping, but it will not be able to take off. There is no onboard control with this system. So in order to do this, we broke it down. Okay, we made a lot of progress with vehicle design. Okay, so we reinforced our actuators. We were able to use all of the input to output energy necessary. We also thought about scaling the vehicle up, to this more hot moth size system, but the trade-off between force generation and input power was very unfavorable. So we went back to something smaller. We also thought about all of these sensors that we could put on board the system. Okay. I'm not going to talk about this sensor. This was the first sensor I ever put on board RoboBee. But I like talking about it with grad students just because this was a very dumb decision that I made. I soldered directly onto the sensor. There's no PCB here. It's just wires directly attached to the leads of the surface mount component. Also, it's sitting here on the belly of RoboBee. It's never going to take off if you put 20 milligrams on an 80 milligram vehicle, right at the front. But you live and you learn. And this also went to aircraft, so it was fine. Swing for it. You may hit, and also you can look back on your past and see this was really dumb. The rest of these I'll talk about later. Also thinking about control and power autonomy. So this was power autonomy. And then I worked with a group who did custom ICs, who built a custom brain chip here. So this also has a Cortex M0, but it also has customized accelerators to accelerate some of the functions that we're using regularly. So this is a lower power option compared to just using a standard off-the-shelf microcontroller. This is a power IC that basically took this entire setup and popped it into one IC instead of using all of those off-the-shelf components. So how do we make these things? We use mesoscale manufacturing methods. Every single component here is built in my lab. My students are now very proficient at designing and building things in this way. It has two transmissions here on the side that translates this back and forth motion that you get from PZT actuators into this back and forth motion that you have with your wing stroke. There is a wing hinge that allows for passive pitching. So you can kind of get this nice oar stroke. Two piezoelectric actuators, motion tracking markers, everything that we do is done inside of Vicon at the moment. 4 legs to allow the vehicle to stand. And again, it is tethered. So there's an electrical power cord and an electrical plug. Wings are made out of 1.5 micron polyamide plastic. And then the spars are just custom carbon fiber prepeg that we make in lab. In order to fabricate these things, we have a laser system, the LPKF ProtoLaser U4. It has a spot size of 20 microns, so we can get very fine resolution on our system. We pre-pattern every single layer. So we'll have rigid layers, which provide structure. And then using 2 layers of adhesive, we will adhere a flexible layer in between these 2 rigid layers. Okay. By exposing this flexible layer, you get a hinge. Okay, you can start to bend. And once we heat press and align it, we release this out and we have this foldable hinge. Okay, if we are using castellations, generally that's because we want to fix the fold. You can also not use these castellations, just have straight across motion, and that's more for our wing hinges. Okay, something that's going to regularly move through the system. You just don't want concentrated strain points. all of our systems, this is like the most basic thing you can build. This is the first thing that I teach my students how to build is how do we build a hinge? Once you can build a hinge, you can stack these things in series or in parallel. You can make a transmission. Once you can make a transmission, you can make a leg. Once you make a leg, you can build a robot. So this is the methodology. Most of the robots in my lab are being driven with piezoelectric bimorph actuators. Why? They're small and lightweight. They're around 20 milligrams. They fit on the tip of my finger. They're high energy power density, so about 2 watts per gram. They also have a wide bandwidth range, so I can operate them anywhere from 1 hertz, which can be good for, you know, a slower scale crawler, or I could go up to 1,000 hertz. I have no robot that is operating at 1,000 hertz. But it could if we wanted it to. Most of our robotic vehicles are operating around 165 hertz at the moment. It's a bimorph just for amplified output motion. There's this top plate of PZT. We send a steady high voltage line to it. It's about somewhere between 200 and 300 volts. If you send a sinusoidal signal through this central layer and you ground the bottom plate, you're constantly varying the electric field between these 2 plates, and so you get bending and contraction in opposite phases. So you get this cyclic back and forth motion. Excellent for flapping, excellent for any type of leg dynamics, right? It's great for swinging. It's really difficult to get rotary motion at this scale, okay? Because you can't use gearing, everything will stick and stay. So we're always thinking about ways to get reciprocal motion in our actuators, reciprocal motion in our hinges. We then do a lot of 2D, 3D CFD, and then do validation with PIV. So we can actually see how the vortices are being created and then shed to give us our propulsive force. We can do this in air here, but also if you flap it at a lower frequency and you think about Reynolds number scaling, you can also operate these systems in water as well. So you're not just limited to one type of fluid. How do we assemble the vehicle? Tweezers and glue. Okay, a lot of grad student hours, a lot of my hours. Everything kind of comes together in puzzle pieces and then gets assembled under a microscope. Using basically the same methodology here. There's a couple more jigs that are being used here than are used in our system, just because we have more press fit components at the moment. But yeah, this is how you assemble one. It takes a lot of practice, a lot of skill. One of my students is on this call and they could vouch for how much effort it takes to build one of these things. I love it. I wish that I could be doing more of it. But sadly, the life of a professor just means that you don't have time to be in labs under microscopes. Once we do that, we characterize the vehicle. So each wing is independently actuated. We never actually operate them at different frequencies. We could, and it could be useful for something like yaw control where you want to spin in place. But for the most part, we flap them at the same frequency. We test the vehicle. This is on a cantilever beam on a capacitive force sensor so that we can estimate the forces along each side. We can absolutely generate pitch, roll, and yaw torques as well. I mean, pitch, you just change your mean stroke angle. I mean, my body just did it. If I throw my wings forward, my body goes backward. If I throw my arms forward, my body goes, if I throw my arms backward, my body goes forward. Same principle here. Roll, if you flap one wing harder than the other wing at a larger amplitude, you will move, okay? You're generating slightly more force. Yaw, this is the old method of generating yaw. There's a professor, Professor McGill, who came up with a new method for yaw control and operating slightly away from the resonant frequency. You can do more of the split cycling that you see here. The problem with split cycling, where you flap your wing faster and then slower, and then do the opposite on the other side. This is a second order dynamic, and our transmission perfectly filters that out at resonance. So you don't actually get any of this yaw authority that you thought you did. But if you operate away from resonance, you can do more yaw control. So what do? We build the system, we've tested it individually, now we just start taking it off. And because every system is hand built, We do this open loop testing again and again and again until you get that straight up motion. Okay, so we basically tuned out any asymmetries in the controller. Once we do that, we wrap an adaptive control strategy around the entire system. So we have our angular controller, which is controlling pitch, roll, and yaw torques, and then we have a lateral controller and a altitude controller on top of that are operating at lower frequencies. But again, everything is coming through this very fine tether here. So this is 54 gauge mag wire, very, very thin. This is 4 wires actually all bundled together. And then there are these 4 Vicon markers here. So nothing is being done on board. There is no compute. If we scale back, everything is done inside of this Vicon arena that you see here. Just for scale, that's the RoboBee. This is a quarter. And then if you move even further back, it takes an entire room to control this. I don't know why it's so grainy. We'll survive. It takes an entire room to control this. So I have my Vicon computer is here. It's capturing position and orientation data at about 500 hertz. That information has been being sent over, honestly, RS-232 to a real-time target machine. We use the speed goat in my lab. This block diagram that you see here is the controller, right? It's modifying all the control signals in real time. The low voltage signals that are being generated by the computer have been sent to the high voltage amplifiers, which are stepping the power up to 200 volts. And then the back of these amplifiers gets routed all the way to here, through this wire, through this tether to the beat. It just steps through all this until you finally hit the beat. Okay. So the thing that we do in our lab, especially on the ECE side of things, is how do I take this room and minimize it to a flex PCB? So current state of the system, RoboBee trapped inside of a Vicon arena, it can only fly for about 1 cubic foot of flight space. So we explore all these various components. Okay, we think about what sensors can I use? Can I build something custom? Can I use something off the shelf? Also thinking about new vehicle designs and then new power strategies as well. Okay. We'll talk about how do we actually achieve sensor autonomy, which hasn't actually been done yet, and then power autonomy, which has been done with a caveat. So, current sensing system, off-board motion capture arena. Sensing modalities, we have position and orientation, feedback of about 500 hertz, latency of about 20 milliseconds. Okay, so we're getting information at the rate that we need to. I mean, we're well over double flapping frequency, but we're constrained to this like 1 cubic foot of flight volume. But this is kind of a baseline, right? So I know that if I get a sensor that can give me feedback at 1 kilohertz, it's going to work. We thought about this as training wheels for the vehicle, which was a funny joke like 2 years ago. It's less funny now, I'm sorry. So what was our sensor shortlist at the time, right? Remember, this vehicle only had a payload capacity of about 40 milligrams, a wingspan of about 3 centimeters, flapping frequency of 120 hertz. So we want to be, some multiple over that. We're seeking sensors that have less than 5 milliwatts of power. This is actually an incredibly difficult ask. Attitude bandwidth, somewhere around 100 hertz, right? Because that's, about the feedback frequency of our attitude controller. And then lateral bandwidth is actually much, much lower. Okay, we can provide feedback at a much lower rate and still maintain some relative orientation. The vehicle is super unstable in pitch and in roll, so you constantly need to be providing that feedback if you want to remain upright. So in custom sensing, right, these use ocelli. These are sun compasses, so they can orient themselves relative to the sun. This is something very similar. We just use phototransistors, okay? And by taking the differential signal between 2 pairs, we can estimate the orientation of the light. You can also do very small scale IMUs. This was the magnetometer that I first worked on that I talked about. This is an InventSense MPU 9150. So this has, this company still exists. I just don't think it's called InventSense anymore. But this had a 6-axis accelerometer and gyroscope, and then a 3-axis magnetometer that operated at about 80 hertz. But if you guys have ever worked with these things before, if you're inside of a laboratory environment, everything is giving off magnetic fields. So unless you are creating an external magnetic field, you cannot use a magnetometer. Proximity sensors. So this was back in the day before they made the time of flight sensors. So this was just taking the absolute amount of IR being reflected back. Since then, time of flight sensors have come out. They're super precise. You can get down to millimeters of accuracy if you're close to the ground. So our lab still uses that. Optic flow sensors. This was a custom device created by Jeff Farrell, who just made very low resolution cameras. So it's just detecting relative velocities on this relative to a pattern. This is an endoscopic camera, 1 millimeter cubed. This is actually just used from minimally invasive surgeries. There is an entire market for these small scale cameras. It is very small, but it has 250 by 250 pixels. It can do RGB imaging. Back then, this was using low voltage differential signaling. Now it has SPI components as well. So this is an active area of research in how to actually perform low compute with these images, because any small scale microcontroller that I put on board does not have sufficient RAM to save even one image. So how can I actually downsample this? Active area of research. This is an older version of an antenna with a strain gauge, but the principle still applies in some of the work that I do today with capacitive or resistive sensing. And how we can actually detect changes in our environment, either through wind or through water, other means. So 2 demos, because I feel like these talks always go better if you just show videos. Here, the sensor is just sitting on the top cap of the vehicle. This is the InvenSense 9150. It weighed approximately 30 milligrams. We first just wanted to make sure that it could take off. It absolutely takes off. Now it's just trying to hit this set point, okay? It begins drifting after about a second. It's able to recover, but then after about 3 seconds, the integration error that is being accumulated from the gyroscope is too high, and the vehicle just falls out of the sky. I mean, it fell and it landed perfectly, which was not commanded. And we were very lucky, and we just took off again on the next flight. But we need additional sensing strategies in order to handle orientation, right? At this point, at this stage in my career, the bee could only carry 40 milligrams. So if I had 30 milligrams of payload on board, I didn't have another sensor that I could put on board. So I stopped working on this. The other sensor that I talked about, there was this time of flight sensor. At this point, I also learned that if you put a very thin Kevlar thread on the top of your vehicle, you can just hang it in your arena, and you don't have to stress out about the fact that at the end of all of your experiments, your vehicle's just going to fall out of the sky. So the tether isn't actually doing anything on the top. You can't even see it. I didn't even have to spoil it. And here I'm literally just sending a proportional controller to say hover around the set point, so you can see it just oscillating over that line. But there's a small time of flight sensor on the bottom, okay, that's detecting distance from the ground. So what do we need to hover, right? We need to think about sensor combinations. Simple sensor combinations, we can stabilize attitude with the gyroscope. This obviously is not going to hold for more than a few seconds. We can incorporate accelerometer measurements to compensate for integration drift, but these can get really noisy because my vehicle is vibrating, right? And so I'm just eating that noise. I can also keep some fixed altitude with proximity, right? So the VL6180, which I think is the one that I'm using here, I mean, it gives feedback at about 40 hertz, but again, the latency needed for altitude dynamics very low, or higher than needed. If I combine these two things, total mass 53 milligrams, power 8 milliwatts, total dimensions 5 by 3 by 2 millimeters. This was something that wasn't prep in 2021. I didn't realize that I had done this. And then other groups had started working on this problem. So like Guido DePrune and Sawyer Fuller had been thinking about, sensors to stabilize flight for many, many years. And so, I mean, I started to think like, okay, if I can apply their work and not do the same thing at exactly the same time, then that is what we will do. So we switched into this other area, which is something that we're still thinking about, which are cameras for exteroception. So you can't actually see the camera on this. It's on the other side of this actuated mechanism. And so this is actually something that I worked on with Nick Gravish originally, where bees, when they approach an obstacle, they'll keep their head fixed, okay, looking at the obstacle, and they'll move their body around it, okay, so they can constantly get this straightforward motion. They can get the information that they need. So here what we were doing was we were keeping the body fixed, but we were changing the position of the head as it saw this checkerboard pattern moving, okay? So we have this additional actuator. It moves significantly more in one direction than the other. That's just a problem with asymmetric stiffnesses that we can deal with later with the hinges. But everything, again, it's, you know, we have this tether that is wrapped around it that is then going off board. So something I'm working with one of my current students is just thinking about how to actually integrate this with low compute, okay? What we're doing, instead of using checkerboards, we're doing something even simpler. We're just going to beacon our environment. Just throw beacons and tags, active tags into the system, downsample and threshold our images that way. That way we only need to compute, you know, 4, 6, or 8 spots and estimate codes from that, which I'm sure you guys know how to do. But could you do it with, you know, no RAM? That's the question. Okay, so we haven't yet achieved sensor autonomy. We've started to narrow this field down. There are a bunch of people working on this problem. But if we don't have power on board, we can't actually put any of these sensors on board. We can't actually do anything. So halfway through my PhD, I switched into thinking about power autonomy, okay? Because I wanted to know what I needed to do to get these robots out of the lab. So what are we doing with power? So we need to increase payload capacity. That's the first and most important thing. So we need to increase our thrust while also considering the overall weight and power of the vehicle, okay? If I can increase thrust, right, but it's going to, you know, linearly increase my power, that doesn't work, okay? I'm in the same position that I was before. And I also just don't want to increase the size of my vehicle. So what we did was we increased the actuator and the transmission stiffness, which led to a very pronounced resonance, somewhere around 165, 170 hertz. Which put us in this new operating condition. And we play this video, which you're not really going to be able to see. It's flapping its wings, but it's only flapping its wings through like plus or minus 20 degrees. Okay, so a very low flapping frequency, flapping amplitude. And that's just to carry its own weight. So the idea here is that like if you have an even larger flapping amplitude, then you could carry more weight. This is kind of how we measure forces at this point. The overall load, so thinking about power autonomy, what amount of power are we consuming? We've got about 28 milliwatts of real power, 47 milliwatts of reactive power. So this is just power that is being consumed by the capacitive element inside of the piezoelectric. Total lift capability of this vehicle is about 270 milligrams. So we go from 40 to 270. We went from 40 to 170 in payload capacity. And our signal increased in voltage slightly. So, you know, up from like 150, 160 to 190. And then 170 hertz. The note about it being unipolar is super important because I'm not generating 170 hertz signal, like plus or minus, right? I need to shift everything to some mean voltage and then operate between 190 and 0 the whole time. That is an annoying thing to build. And we're going to step through how we actually do this. So if we think about our control architecture, right? For the purposes of this talk, we're not really going to be able to talk about some of the controllers that we thought about, but I'm happy to talk to anybody one-on-one or talk to you about it over email some other point. We've talked about, you know, different sensors that we need for the motion tracking system, but now we're thinking about, okay, I have a waveform generator and a D to A converter, okay? And I need a high voltage amplifier, okay? So I have a microcontroller that's going to determine what my next signal should be, and then it's also going to need to generate those signals. And then I need a step-up converter that is going to move from 3 to 5 volts that my battery is operating on, or my solar cells are operating on, and step it into 200 volts. So first we need to generate some high voltage time varying signal. Again, this is kind of the output motion that we're looking for. If I take a cross-sectional image of what this PCT actuator is doing, right? I have a high voltage bias line that is being put on the top of plate A2. Current is, or the field is moving through the plate into this central layer, right? Which is getting my sinusoidal signal. And then I have between the signal layer and ground, I have my other plate, A1. Okay, so everything is moving in the same direction. Carpelson, well before I started my PhD, came up with this dual stage topology where you have a tapped inductor boost converter here on this side, and then you have this like half bridge switch phase. Okay, so you using pulse frequency modulation. So if I'm consuming a lot of current to like during these like sharper slopes of my signal, I'm going to need to pulse more frequently to keep a stable bias line. Okay, so that's the pulse frequency modulator that you see here. That is just controlling this switch Q. Okay, so I start with some primary signal. I then move through my primary and secondary transformer, and I store all this energy on this high voltage capacitor. This is the heaviest component on the board by far. Once we have a stable system, we can then draw current through these switches. So we can close the high voltage signal, pull the voltage on the output up. We can also pull voltage from the actuator down through QL, right? And that lowers our system, right? So we're always pulsing in sequence, right? So we have QH pulsing when we want to rise, we have QL pulsing when we want to fall. Okay, so we need to build this using off-the-shelf components, and then I also need to find a microcontroller that can pulse at a high enough frequency, right, to stabilize that top line. He estimated in 2011 that it would take about 100 milligrams to build this, and that the input power would be about 100 milliwatts, okay? So if you have a 25 milliwatt load, given the piezoelectric actuator size that we have, so 4.7 nanofarad approximately, this is the amount of power that you're going to consume. So like any respectable researcher, I was like, fine, I'm going to build it and see how close he was to being right. Oh, but before we do that, okay, I have 100 milliwatts of power. What are my power options? Okay, so custom batteries. I worked with Professor Duduta, who came from a battery startup after his PhD. And so I said, okay, can we build custom batteries using this laminar manufacturing technology? And he was able to build a few that were able to give me approximately a kilowatt per kilogram at a mass of about 100 milligrams, which is what I asked of him. But when we actually scaled it down to a usable size, it either wasn't able to give me that power, right? So once we had removed all the packaging, right? Wasn't able to deliver that type of power density, or it could, but it could do it for a fraction of a second, right? It was no better than a supercapacitor. Other very strong option, photovoltaic cells. You can buy these off the shelf, you can buy them in offcuts for super cheap. This is actually devices from Microlink. This is a centimeter. You can wire them in series and parallel to your heart's content, right? We'll just sell you one individual cell. Each cell weighs approximately 10 milligrams. It has an efficiency of about 30%. Each cell in one sun give you about, you unplugged so long. Each cell can provide 10 milliwatts, okay? Just with one single sun. So power autonomy, very simple ratio, okay? Total lift has to be greater than mass of the bee, the mass of the power source, and the mass of the drive stage. Total power, obviously, your input power has to just be less than whatever power your source can provide, okay? It's incredible that my entire PhD rested on, 2 inequalities. So based on Carlson's measurements, right? I have a vehicle that can lift 270 milligrams. My vehicle weighs 75 milligrams, set in stone. Nothing is changing here. My source, I was like, okay, I could use 6 of these cells, right? 60 milligrams. And I've got 100 milligrams from Carlson's estimate. Okay, so this holds. This inequality works. I can cheat and say, okay, I'll give myself 120 milliwatts of power, right? Based on his estimate, and just provide 2 cents instead of 1, right? I can get a really fancy light source. Totally fine. I can do that. Okay, so I'm gonna build this. I'm gonna test and see if it works. So with discrete components, I built these power electronics. So the total mass of these electronics was 185 milligrams. That also includes these 60 milligrams, so 125. He was only 25% off in his estimate, which I'll give him credit. A lot of that was due to the input capacitance that was needed to stabilize the low voltage signal from the solar cells. Okay, so 20 milligrams came just right off the bat. They actually right here, you can't tell because this is a 2-dimensional image, but I just started stacking capacitors on top of each other with like the leaning tower of Pisa. I had, I think, 5 or 402 capacitors just stacked on top of each other. So the board was no longer flat, it was like raised in a really uncomfortable position. The dimensions of this were 10 by 18 millimeters. This was a 2-sided board. You make it longer, you make it smaller. And people are interested in the dimensions, but I don't think it matter that much. Total input power was 150 milliwatts. 30 milliwatts of that came from microcontroller unit. And that was just because I was operating it at the fastest clock rate necessary. And that's because I wanted such fine precision on that high voltage bias line. Boost efficiency was about 68. Overall efficiency was 19%. So not what I wanted. I did demonstrate that you get the exact same flapping kinematics. So I would have achieved the same amount of lift that I did before, but it wasn't going to fly. That wasn't a joke, but it actually wasn't going to fly. So another way of doing this with lower mass, instead of using a tap conductor boost converter with a half-bridge switching stage, you can use something called a boost flyback. Okay. This is just significantly lower mass than before, just because you're using slightly fewer components. If you, instead of using something that is unidirectional in its field, right, and you basically flipped one of these plates so that the field wanted to orient towards the signal layer, right, then I could just take one of these flybacks and double it, okay? The only thing I have to do, I can get 2 signals, right, that are working out of phase with each other. But that's not the way our actuators are built, or at least that wasn't the way the actuator that was in the vehicle was built. And so we had to come up with a new strategy to prevent depoling, where VA is always larger than VB. So we came up with this unipolar switching strategy where VA is being pulsed in this first phase, and then it is just following VB. And then we have VA, and then it follows VB. VB is clamped here. So you have the full spread of VA, right? And then VB also gets the full spread here, and VA can just follow that spread. Okay? But what the nice thing about this is that everything now is sequential, right? It doesn't take any specialized control. I can just open loop say pulse QLA, pulse QHA, QLB, QHB. Okay, so I can just now start just running this in open loop. I can get a much dumber microcontroller in here. I then have a switch here on the bottom to clamp VB. That switch is just right here. So it holds it to ground whenever I'm pulsing VA. Clamp VB, sequential plate switching. Perfect. So comparing the dual stage to the flyback, which is the single stage, right? I can now provide 2.5 suns instead of 4 suns, still off of my 2-sun estimate, but we'll survive. My total mass, I decreased it by about 34 milligrams, which took a ton of effort. But you know, we have this very nice board here on the bottom. Total dimensions are slightly larger, but that's because it's a single-sided board. I started manufacturing these boards in-house instead of waiting weeks for Flex PCB to come back. With all the capabilities that I have in the lab, I can build these, in a couple of hours. Input power decreased from 150 milliwatts to 110, again, because I got a much dumber microcontroller on there, and increased overall efficiency from 19 to 25%. Okay, so the person that I was working with, Noah Jaffrez, at the time, was like, can you do any more to decrease this? And I said, absolutely not. I am out of ideas. So I showed him the waveform analysis. I showed that, yes, we're pulling, our overall voltage down, but I'm still able to hold it for the most part, somewhere between 4 and 6 volts. I'm not at my ideal waveform. There's this huge step at the beginning where I'm just dissipating a lot of energy. But I have a dumb microcontroller. It's what I'm capable of. But if you actually look at the harmonics, I'm pretty well matched to what we wanted to be doing. So we put it on the 2-wing vehicle. I stared at this video, I want to say, for a couple of hours, where I said, did it take off? Like, I looked at it and I was like, it started here and it is here, so it took off. But this convinced no one in my lab at the time. And this, I was like, well, what about this? And they were like, no, like the Kevlar thread, I saw it like pulled and pulling the vehicle up. So like, fine. But at that point I was like, I'm done redesigning the electronics. I don't think that there's anything else we can eke out in terms of performance. So we went back to vehicle redesign and we came up with the X-Wing. So new actuator design increases our total force production. So here we have alumina bridging the PZT plates here on the front and the back, and this just prevents any spreading between the base and the plates. So all of the output motion is being directed to the output of the wing. Because we've increased the force, we're about to linearly increase our total power consumed. P is equal to F times V. So the only way to keep power constant or to diminish it is to decrease our wing velocity. Okay. Really good way of doing that is just to move from 2 wings to 4 wings. So we come up with the X-Wing. Why does that matter? If you have 2 wings, right, you need to move through a full amplitude every stroke. If you have 2, you're only moving through half that amplitude, okay, with the same frequency. So this vehicle, 90 milligrams, same amount of power consumed. Total lift now, though, is 325 milligrams compared to 270 before. Actuation signal is a little bit higher. It's 195 instead of 190, and I have 165 hertz. Kept the center of pressure at approximately the center of mass that I could just take off open loop. And we have our first untethered flight. And if you went out to lunch with me, you know how much I hate this video just because that wooden block there. My only advice, if you guys are PhD students, is pretend like the video that you are taking is the only video you will ever get in your entire life, because sometimes that will be the case. This wooden block was actually just marking the start position, like we were just scribbling red marker on it, and it was holding the light up. So I was standing over the light, flicking the light on, and just hoping that the bee was flying. I couldn't see it as it was happening. But yeah, as the light comes on, we get power in the photovoltaic array. Our, boost flyback converter is generating the signals. The same signals are going to both wings. I have no control on board. I can control the pitch angle to an extent because changing the mean voltage signal, that's easy to do. But I have no independent control over each wing. Okay, so this was the first takeoff. Nature enjoyed it. They created this GIF of our work. It was the first untethered flight of an insect scale microrobot. Total mass was about 259 milligrams. Input power was about 3 suns, 2.5, and we demonstrated passive stability. Calling it RoboBee X-Wing, the title of the paper being Flying Solo, and it operating in 2 suns, made me very concerned that we were going to be sued by Disney for all the Star Wars references we threw into one publication. We never heard back. And so I just don't think they know about it. And we'll continue to pretend like nothing has ever happened. Thinking about how do we go outside? So alternating drive actuators, right? And we have sequential drive actuators at the moment. If I have alternating drive, I can get rid of that one switch, which is really dissipating power through 200 volts. Also thinking about multi-layer actuators. So the amount of field that you need to apply for a certain displacement is based on the PZT that you're using. If you have the PZT thickness, you can have your voltage signal from 200 to 100 volts. This increases the boost efficiency from about 65 to 75%. It reduces switching losses greatly in drive because power goes with V squared. And could reduce overall system mass by about 10%. Okay, haven't actually built this yet just because it's already very difficult to work with PZT. It's even more difficult to work with half the thickness of that PZT. So something I'm super interested in doing, but have not yet started. Also creating a new vehicle design. So if you read the supplemental material in the Nature paper, you'll get to these 9 subplots, subfigures, and you'll notice that under no circumstances are we ever going to achieve autonomous flight with this vehicle. We're still our metrics just don't quite match up. So we still need to go back to the drawing board for a new vehicle design. Also thought about IC work, and I'm not going to get into it just for the sake of time, but power ICs and brain ICs, again, technology is moving so quickly that a lot of what we can just buy with off-the-shelf microcontrollers. There's Cortex M0s, M4s that have significant amount of RAM on them that are now at wafer level chip scale packaging that we can throw on board. I did fly this once. It never flew again. You can see me in the background looking incredibly bored in this video. Pretend like every video you're ever going to take is going to be the only video that you're ever going to take. So make sure that you're not sitting in the background confused about what is happening in the day. This was the 15th flight that we tried and it finally took off, and we were very excited about it. Okay, so what are some cool new things that are working on in the lab? I'm just going to spend 2 minutes on this just for time's sake. Scaling effects. This means that forces that we neglect at macro scales become particularly important at small scales. So we see water striders are able to sit on the surface of water. Ants can climb on walls, they can climb on various surfaces. Once you get down into the microscale, cilia and non-reciprocating motion become really important for swimming. You can, utilize viscous effects in air to float, and then even spiders will, create webs and spin and take off and fly. Locomotion on water, something that's super important. I guess it's not important, but it is an interesting capability that we can see at this scale. So here we have legs that are kind of using this oar paddle method to continue pushing along the water surface. You can also impulsively jump from the water surface. And so a lot of roboticists have been doing this in the past, where you can see clear takeoff. There's also an interesting capability called interfacial flight, which a couple of researchers have been doing in the past, where beetles will stick their legs into the water and then begin flapping their wings above the water surface. I did not take this video, so I won't apologize for the quality, but I did blow it up. They'll flap their wing along the water surface to generate momentum across. This is something that we're doing in our lab with building the Gamma bot. So if we just do it at 1x, we can design a strider that can move across the water surface. If we slow this down, we can also achieve same idea, but you can see how as we flap, we create these ripples. These are passive legs that are sitting on the surface. So we've decoupled, the amount of payload needed to stay on the water is entirely based on the length of the legs, and the amount of force that we can generate just allows us to propel forward. We can also turn. Thinking about power autonomy, thinking about control design, thinking about characterization of flight design, payload capacity, and maneuverability. I also worked on the combustion jumper with Cameron Aubin. This was recently published in Science. Also thinking about underwater locomotion strategies, new crawling platforms. As we scale down, the amount of force that we can generate holds actually, and so we can carry the same amount of payload on a smaller scale system. And then thinking about new centimeter scale fabrication. I'm not going to play it. So I want to thank all of my students and my collaborators, especially the students who are on this call. I didn't realize that they were doing that. New and old professors at Cornell. He's going to go to Michigan this year. But yeah, that's it. So.
Thanks for the fantastic talk. We can open it up to questions, both in the room and online.
Have you gained insight into like nature's like insect like leaf flapping wing from rebuilding it from artificially? Like how close are you mimicking like the true bee flap versus like?
Yeah, so we're not actually mimicking it that closely with this vehicle. So bees, the way they flap, right, they have one main power muscle and then very small like control muscles that change the angle of attack during flapping. What we have is two independent, power actuators almost, and we're kind of passively allowing for rotation. We don't have that like very tight control. That's kind of where you trade off, like what is the ease of building your engineered system versus, doing biomimicry. And so we kind of decided that not adding additional actuators will save me power. And I'm nimble and agile enough that I don't think that I need them. Yeah.
I've got a question. So as far as the sensors you need to stabilize your vehicle, I guess like some vehicles or maybe even some animals, I'm not sure, have like passive stability just because of their mechanical properties.
Absolutely.
Is that something you're thinking about at these scales as well?
So it's not actually something that we want to think about at the insect scale, just because we really appreciate the maneuverability. Like, yes, I could absolutely like tie multiples of them together, right? And then just have like passive, stability, just because I don't have as much compliance in my angular velocities. But we like the agility of it. So we could add passive sails. I think a long time when I was presenting the nature work, at least in the last few years, because I guess I haven't been able to present on it that often because of the pandemic. But the last time I gave the talk, they were like, "Oh, so you added a sail?" I was like, "No, it's not a sail. Like, it's not actually adding any stability. It's just a mass that is like sitting underneath." But yeah, no, it's something we could do. But yeah, you just diminish your overall agility.
Makes sense.
Yeah.
You mentioned a few times that you need to do a few runs before you can get stable flight. Do you have an instinct for whether that is like just luck, like you need to do it until it works, or whether it's based on how this thing lifts off? Like, are you able to look at a flight and determine whether it's going to fail or be successful before it fails or works?
Oh, if the controller is wrapped around it, it will succeed almost 100% of the time, unless there's some like weird quirk in the system where like Vicon is not properly giving me a reading of what my flight velocity is. It takes a couple of tries open loop so that we can tune out any of those, any of the hand done errors. I can tell at the open loop phase if a vehicle is ever going to fly. Mostly I can see it statically, right? Like if somebody has put it together and the transmission is like bent out of shape so that like one wing is sitting here and one wing is kind of back here, like I'm never going to be able to fly in that way. It's just going to consistently move or propeller in that direction. If you get to the open loop phase and you've kind of railed your signal, right? So everything has to exist inside of that envelope, inside of that 300-volt envelope. So if it takes, 50 volts of pitch torque in order to take off, then I'm not going to be able to actually control my flight. Like I don't have enough room in my control signal. So yeah, no, I can determine that pretty quick.
Any other questions? Cool. All right. Well, thank you so much for the really exciting talk. Thanks for visiting us.
Oh, thank you for having me.